Hey everyone, and welcome back to The Explainer. I am so pumped you're tuning in today because we're going on a seriously cool journey. We're going to track the whole problem-solution evolution of object detection. So we'll see exactly how computer vision went from these incredibly slow, clunky, and honestly totally impractical algorithms all the way to the lightning-fast, real-time modern AI systems we're all using today. Let's get into it. So, to kick things off, we really have to ask the fundamental question here. How do computers actually see where objects are? Think of it kind of like a game of Where's Waldo, but for machines. It's one thing for a computer to just glance at a picture and say, hey, Waldo's in here somewhere. But it is an entirely different, intensely complex mathematical challenge for it to hone in on the exact pixel coordinates and say, boom, he is exactly right here. All right, here's our roadmap for the explainer. We'll start with the core object detection problem, move right into the RCN evolution and the YOLO paradigm shift, define our core metrics, build out an actual Python pipeline, and then wrap it all up with speed versus accuracy.
Okay, Section 1, the object detection problem. Let's get a handle on what exactly we're trying to accomplish. The thing you have to realize is that object detection is actually solving two entirely different subproblems at the exact same time. On one hand, you've got classification, asking what object is even present, which just gives you a single label for the whole image. But then on the other hand, you have localization, which asks where exactly is it and forces the model to spit out a specific set of coordinates. Object detection sits right smack in the middle. It demands both the what and the where, simultaneously. And to solve that where part of the equation, we rely on a specific piece of geometry called a bounding box. Basically, it's just a rectangle that tightly wraps around an object, represented by four numbers, the x and y coordinates plus the width and height. Simple enough, right? But remember, the detector isn't just throwing shapes around. It also attaches a specific class label, like car or person, along with a confidence score that basically tells us, hey, I'm this certain about my prediction.
So, with the core problem clearly defined, let's look at the early, pioneering attempts to solve it using deep learning. Section 2, the RCNN evolution.
You really have to appreciate just how insanely fast this field moved. The timeline is just incredibly condensed. In 2014, we got the original RCNN pioneer. Then, literally just 1 year later in 2015, we get fast RCNN, which was followed almost immediately by a total paradigm shift with YOLO. It was a wild, frantic period of innovation. Let's unpack what actually happened there.
Let's start with that original RCNN from 2014, 47 seconds. That massive number represents the glaring bottleneck of this early system. It took a whopping 47 seconds to process a single image. I mean, you could literally go brew a cup of coffee waiting for your computer to find a stop sign. And why? Well, it used this technique called selective search to generate around 2,000 proposed candidate regions, warped every single one to a fixed size, and then passed all 2,000 regions through a convolutional neural network entirely independently. It was a clunky, multi-stage, horribly slow process.
So, fast forward to fast RCN in 2015. The engineers realized all this redundancy was absolutely killing them, so they completely flipped the script. Step 1, pass the full image through the deep CNN just once to get a shared feature map. Step 2, run the selective search for the proposals. Step 3, project those proposals directly onto that single, already computed shared map. And step 4, this is the real magic trick, apply region of interest or ROI pooling to extract a fixed 7x7 feature per region. Just like that, they completely wiped out all that redundant computation.
The result? A massive, massive drop in processing time. We went from 47 agonizing seconds per image down to just 2 seconds. That is 25 times faster. Plus, fast RCNN allowed for end-to-end training. They combined the classification and bounding box regression into a multitask loss function, using a really clever mathematical trick called smooth L1 loss to keep outliers from just totally wrecking the calculations.
But here's the thing. Even at 2 seconds per image, fast RCNN just wasn't cutting it for real-time video. And that brings us to Section 3, and the massive paradigm shift, you only look once, better known as YOLO.
YOLO was a real game changer because it completely reframed object detection as a single regression problem. It just outright ditches those 2,000 region proposals we were just talking about. Instead of classifying regions one by one, YOLO predicts all the boxes and their class probabilities directly in a single forward pass through the network.
To really get why this is so cool, let's juxtapose the two approaches. The old way was two-stage: propose the thousands of regions, then classify them.
The YOLO way is one stage. It just divides the whole image into an S by S grid. Each grid cell is then put in charge of predicting bounding boxes, along with the confidence scores and class probabilities. Everything gets output in one giant tensor, mathematically represented as S by B times 5 plus C. It is elegantly simple, and man, is it incredibly fast.
Now, once we have all of these boxes being generated, we run into a new problem. How do we actually know if they're any good? And what do we do about duplicates? That brings us to Section 4, Core Metrics, specifically diving into IOU and NMS. First up is IOU, which stands for intersection over union. Honestly, this is the absolute most important metric in object detection. It strictly measures the overlap between the bounding box your model predicted and the actual ground truth box. The math spits out a score from 0, meaning absolutely zero overlap, to 1, meaning it's a perfect match. By industry convention, if your IOU is greater than 0.5, we generally consider that a true positive detection. Now, because YOLO is looking at a grid, it's notorious for predicting multiple overlapping boxes for the exact same object. To clean that up, we use non-maximum suppression, or NMS. Here's how the looping logic works. Step 1, you sort all your boxes by their confidence score. Step 2, grab the highest score box and lock it in as a final detection. Step 3, look at all the remaining boxes, and if their IOU overlap with our chosen boxes too high, just throw them away. Step 4, repeat the process. It's a ruthless but brilliant way to filter everything down to just the single best box per object. All right, let's take all this theory and actually put it to work. In Section 5, we're going to look at building the actual Python pipeline. What's genuinely amazing here is that you can build a highly effective pipeline using just the OpenCV DNN module. And get this, you don't even need a GPU. You just load your pre-trained YOLO weights and config. You pre-process your image by converting it into a 416 by 416 normalized blob. Push it through the network with a forward pass. Then you simply filter out the weak detections using a confidence threshold and apply OpenCV's built-in NMS boxes function to clean up those overlaps we just talked about. It is an incredibly practical setup. However, I've got to warn you, there are definitely some common pitfalls that will absolutely trip you up in Python if you aren't paying attention. First, confusing your box formats. You really need to know if your code is expecting corner coordinates or YOLO's internal center X, center Y width height format. Second, if your NMS threshold is set too high, you're going to keep duplicate boxes. Third, a low confidence threshold will just flood your screen with false positives. And finally, do not forget the YOLO outputs normalized coordinates from 0 to 1. And always remember OpenCV reads images in BGR format, not your standard RGB. It sounds simple, but it gets people all the time. Okay, we've reached our final section, Section 6. It's time to synthesize all this knowledge into some real-world engineering decisions by looking at speed versus accuracy. Looking at the options, your choice of architecture really depends entirely on your specific real-world stakes. If you're doing something like medical imaging, you probably want faster RCNN. Yeah, it's slow, but the accuracy is the absolute best. And in that scenario, speed isn't the priority. But if you're deploying to a Raspberry Pi or some edge device, you want YOLO V8N, the nano version. It's the fastest option out there and still gives you really good accuracy. And if you need a solid mix of fast performance and state-of-the-art accuracy for benchmarking, then you bump up to the larger YOLO V8X model. And you can see the relentless engineering focus of the YOLO architecture over time just skyrocketing the frames per second. YOLO version 1 achieved a very respectable 45 frames per second. By version 2, they hit 67, and with modern iterations like YOLO V8, we are seeing speeds absolutely rocketing past 160 frames per second. I mean, that right there is the definition of high-performance real-time capability. So, we've traveled from the incredibly slow 47-second processing times of the early RCNs, right up to the blazing fast, elegant math of modern YOLO networks. Now that you understand the underlying mechanisms, the bounding boxes, the IOU math, the Python pipeline, I want to leave you with this final thought. How are you going to deploy this real-time detection technology in your own edge devices or apps? The tools are all there, literally at your fingertips, ready for you to build something amazing. Thanks so much for joining me on this explainer, and keep learning.